Unmute. Here I am. Can you hear me now?
Yes.
Now you can hear me now. Great. Okay. And I'm just gonna you can see my screen. I'm just putting it in presentation mode here. Okay. Can somebody confirm that you can see my entire screen here, not my presenter screen?
Yes.
Great. Well, thank you very much. I am going to present to you on the low-cost small sensor project we've been pursuing here in Atlantic, and a lot of you on this call are already aware of that project, so it'll be an update. But for some maybe haven't heard about it, hopefully we'll cover that ground as well. The work is, of course, a compilation from our entire team. As this project progresses, the entire Air Quality Development Atlantic team has made use of from their expertise. So that would be Robert Keenan, Al Wilson, Andrew Tickles, and Lisa Langley. So for some background, the US EPA has been at the forefront of small sensor technology research for about 10 years now. The AQ Spec, or Air Quality Sensor Performance Evaluation Center, which was developed by the South Coast Air Quality Management District in California, they developed an entire testing and evaluation program for commercially available low-cost sensors. So they do non-endorsed field and lab evaluations of various low-cost sensors. So you can see here, this is their test chamber in the lab for purple airs, which we'll talk a lot about in this presentation. Then they give these reports publicly available online that we have made a lot of use of. So usually one of our first steps, to be honest, when we're trying to look at a new manufacturer is we'll go first to AQSpec to see what they found. Because like I said, they'll do it in their lab, but they'll also do a test in the field. So it's very useful information. The US EPA has also developed standard operating procedures, and they've developed platforms, and they have many data analysis and visualization tools. So they have definitely been the forefront of all of this. So these emerging technologies can augment our existing AQ network and provide an opportunity to enhance our air quality services. So our goal is to assess this potential. There are many advantages and disadvantages of these sensors. The advantages are the fact that they are low cost. So they're from dollars to thousands of dollars versus tens of thousands to hundreds of thousands for more sophisticated instrumentation. They are small in size. They're more like palm size versus, something much bigger that might have to be transported by a trailer. They're easy to use. The average public citizen can generally use these sensors rather than having to be a trained technician, which is required for regulatory grade monitors. And there's a ton of information in the scientific literature daily worldwide to be able to tap into. So there's a lot of advantages. There's also some disadvantages. The fact that you get what you pay for. They're lower accuracy and precision. They have limited calibration capabilities, and their reliability is variable. So, of course, one of the main drivers for these, when I say augmenting the network, is, of course, for forest fire smoke plumes. That is the big one. But, of course, they may also be useful for tracking other sources. So, wood smoke, for example, as Barb just described, that's a possibility. So for us here, our focus is to understand the limitations of these sensors, determine their best fit for purpose, and then test their effectiveness. So we've outlined some different phases for our pilot project. The first, of course, is evaluating the sensor technology. So we're evaluating the data accuracy, the sensor robustness, and the regional applicability. So we're looking to see how responsive they are, particularly in the climate regime that we're in here in Atlantic, and then outline their strengths and weaknesses as we test the different options. For the sensors that show promise, we hope to then put them in the field to really evaluate them further. And in parallel, of course, as we do this, we would be dealing with the data, continuing our partnerships. And then our colleagues in the West Applied Science Group, they've actually already been working on experimental products for visualizations and whatnot for this data. So then based on all of those phases, we would then, if they showed promise for a certain sensor, we would consider further deployments, there we go, and ultimately make them hopefully operationally implemented. So meaning so that the data is used by our air quality meteorologists for the forecast program. So the first phase is the testing. So we have been testing a variety of different manufacturers here in Atlantic Canada. Here are some of them listed. The first one, which we are in the evaluation and field study phase, is the purple airs for particulate matter, and I'll talk more about that one. The Vaisala is an example of one that we tried for gases, but didn't meet our expectations. So basically we've called that evaluation ended. That was one we tested that was not successful. The AQ egg, there's some pictures here of the variety of ones. This is the AQ egg. That one's currently being evaluated inside. Admittedly, it's rated for like 0 degrees Celsius. So here in Atlantic Canada, we will put it outside very soon to see how it does, but we may have to make some modifications to do so. But so that's one we're looking at. It measures multi-pollutants, so it does PM and ozone and O2. We're also looking at, we're demoing actually right now in Fredericton with help from New Brunswick Environment, a salivary Cooper. So it's also a multi-pollutant. So it does PM and a bunch of gases. We're demoing that for 3 months. So we've been doing that since December. It's actually coming to an end soon. This one, we'll have to see how it does. It's actually more expensive than most of the others, but we still see that it could be useful. Maybe not as extensively, but to help us with some of our science questions. But it does have a few caveats, like it has to be installed within a certain distance to an FEM or a regulatory monitor for calibration purposes. So we're looking at that. We're also going to look at the TSI Blue Skies for PM. So we have a couple of those. They're kind of more in line with the purple airs. So they're next to install. So purple airs. So from here out, it'll be a lot of focus on purple airs. Because so far for PM, that's the one that we're ready to move into our next phases with a more extensive evaluation. And the main reasons are the data is easy to use, it's open source and it's free. And as you can see, they're widely available. This is the purple air map. You'll see globally they're used, there's a lot available. So we could tap into all of this publicly available data to help us with our evaluations. As mentioned about the US EPA being on top of things, they've already been using purple air data. So this here is a map from them, their fire and smoke map that displays both small sensors and regulatory monitors on one map. They actually started a data view pilot project in summer 2020. So that's where this map came from. And I know it's hard to see, but basically the circles are our regulatory monitors, and then the squares are the small sensors. And then you can actually see there's an overlay as well for fire hotspots. And also note that there's a notice on top of their map that says the sensor data pilot adds a new layer of air quality data from low-cost sensors. Learn more here. So right off the bat, you click on there and it gives you a great FAQ section of why they use them and the strengths and weaknesses, like we outlined. The big thing being these are not regulatory, they're not used for that purpose. So to set the expectation of the data right away. We are very lucky here in Canada to have UNBC working on a similar effort. So in BC, they've developed a map of their own. Here's the link to their website, which also displays the NAPS FEM data as the diamonds in this case, with these small sensors, the publicly available small sensors, as circles. So right now there's just a couple here around Fredericton. There's actually one or more over here now in Shediac, I'll talk about in a minute. But this will, of course, as more publicly available ones come online, they can be viewed here. And they actually apply a correction factor to their data, which I'll talk about a bit as well. So big part of our evaluations involve co-locating the purple airs with the regulatory monitors to really understand their performance. So we are also very lucky to have great provincial partners in the Atlantic provinces who have allowed us to set up sensors at their sites. So this table here shows the data period for those and the locations. So we have 2 purple air sensors at the Halifax site, the Fredericton site, the Wellington PEI site, and Mount Pearl, Newfoundland. And you'll see that we now have over 2 years worth of data in Halifax and almost 2 years worth of data at the other sites. So this is going to give us enough data now to really look at the robustness and seasonal correlations and whatnot. Here is a time series plot from Halifax. So I know it's busy, so just bear with me for a second. So again, remember there are 2 purple air units at the site, and within each purple air unit, there's actually 2 sensors. So you can get an idea of drift even just within the purple air. So that's why there's 5 lines on this plot. So the orange dashed is the FEM, the regulatory, the truth, and then the other 4 are the purple air. So I know this is busy, but it was mainly just to show that in general, qualitatively good, responsive, but in some places, if I zone in on some of these areas, you would see, of course, there's an underestimate or an overestimate of the data. And actually, also stress here the fact that it's exceeded our expectations in its performance really in terms of how long they've lasted. So we really are at a point now where we have to develop a metric for the lifetime of the sensors. So sometimes they'll fail. I'm like, oh, okay, this one's done now. But then it'll come right back online and it still performs. So we basically have to develop a tolerance for these to be able to take them offline when we say they're just not reliable anymore. So we're definitely getting to that point now. Here is the same for Fredericton, but apologies, the color is a bit different. The red in this case, the red line is the FEM regulatory monitor. The other 4 from the 2 purple air sensors at the site. And same, just wanting to emphasize the fact that qualitatively the patterns are the same over time, but of course we have to correct for this over or underestimating. And it's the break point on the break point being where it seems that we need a different correction factor for the lower limits and the upper limits is a big thing we're working on right now. This was from June 1st, 2019 out to November 30th, 2020. So about 1.5 years worth here shown for Fredericton. So we have been doing some statistical analysis on the data. And one of the first steps to understand the data is the distribution. So I know this is a busy plot as well, but basically, and the scales are different. So just the main message here is we're showing again, the bottom 4 rows for all of these sites are from the purple airs. The top is the FEM. So the important thing to note is that the data in general is normally distributed for the FEMs, but different for the purple airs. So more of a one-tailed distribution. So that has an implication for our statistical analysis. So because it's not normally distributed, it's best to use a Spearman correlation rather than your usual, what you see like R² values. So, you know, when we first started looking at this data, we're like, well, why are the R² values so different here in Atlantic? And there's actually a number of reasons for that. Concentrations may have something to do with it, which I'll speak to in a bit, but really, we decided the best way to look at this data is a Spearman correlation because it's a non-parametric test that doesn't assume a normal distribution of the data. So all that to say that these are the seasonal Spearman correlations from Fredericton I'm showing here. So spring, summer, fall, winter, and basically for all the 4 different purple air sensors and against the FEM as the PM 2.5. And the main message here is just that overall the correlations are pretty good. They're best in the fall and winter, and they're slightly less correlated in the spring and summer. And we would hypothesize that here in Atlantic Canada, that's likely due to relative humidity effects. So that's to be determined. So there's a need to correct the data to adjust for the over and underestimates. There are all kinds of different correction factors in the literature and with some of our partners. Some are linear, some are based on polynomial corrections, some use relative humidity and or temperature. And we're just looking for the right recipe for here in Atlantic Canada with our climate regime. So, you know, we have higher humidities, we have maybe different aerosol compositions and size. So we're really trying to drill into looking at those things to find the best possible solution. For now, though, we have the UNBC correction. That's what we're using, the best we know here in Canada. And they have their correction they've built based on co-located data Prince George. So it's a linear correction and it does, it has a breakpoint for 20 microgram per meter cube, so meaning there's a correction for that lower range, a correction formula for the 20 to 200 range, and then a correction formula for the 200 plus range. So on that UNBC map that you go to, the data from the purple layers on that map would use formulas for these ranges. So far we know the sensors are good qualitatively, the responsiveness is good. We really need to know more, like I said, quantitatively. The correction factor is an ongoing science question we're trying to sort out. But it is clear to us that in our statistical analysis, we really need higher concentration data. So when we're thinking, okay, we need a field study to assess this, we need higher concentrations, that comes in, we've targeted New Brunswick. So of all the provinces in Atlantic Canada, we felt that New Brunswick would be good for us to try to capture possible forest fire plumes. There's also, some controlled burns and some wood smoke, as Barb just mentioned, that maybe we could use to capture some higher concentrations with these monitors. And we also have some broader questions from science to look into in the province. So we think the purple layers can help us with some of those. So we're kind of trying to answer a lot of questions in New Brunswick for long range transport, urban versus suburban air masses, local pollution, wood smoke. So all of those things are what we've now called the New Brunswick pilot. While we try to answer all these things, we'll be continuing our sensor evaluations and testing any data corrections we develop. And these goals will be supported by New Brunswick Lung, which is great. We're very excited to be partnered with them. We are also linking in some communication aspects with our Health and Air Quality Services group for AQHI, and of course, ultimately engaging citizen scientists in New Brunswick. So the role of the New Brunswick Lung Association, they will assist us in extending our PM sensors to New Brunswick and help with public education and engagement. And they'll provide education and awareness about PM 2.5 in general, the health effects from exposure, and the use of the AQHI and association of PM 2.5 emissions with forest fires and residential wood stoves. To achieve this, they will be reaching out to possible hosts for the sensors in New Brunswick. And once they have those participants confirmed, we ship the purple layers to them because they're, like I say, just a pocket size that can be shipped easily. They'll be developing and implementing a communication and outreach strategy for the participants, the general public, local governments, and schools who want to engage in this project. They have already created a citizen-friendly installation instructions for these sensors when they're shipped to the hosts. They've created surveys and a Facebook page to engage citizen scientists, and they'll be developing and delivering a related Clean Air Day project in interested schools. So that's for Clean Air Day in June. And then this picture here is showing one of the tweets they sent out to help engage. So they had citizen science opportunity, air quality monitoring, and this is a picture of a purple air at Melanie's house in Fredericton. And so I think that actually helped with the engagement, and we now have a bunch of hosts willing to participate. So the plan is to deploy about 20 purple airs across New Brunswick. The map here on the right shows in green the ones that are already active. The purple X's are the already hosts that have already confirmed in New Brunswick that we have to deploy to. And then the blue, of course, are our regulatory monitors. We're already seeing some initial results showing regional differences due to possibly source and terrain, like wood smoke in the valley. That's just here. I zone in on the 3 around Fredericton, and you can see, this is 47 microgram per meter cube, not an hourly average. That's a snapshot on the Purple Air website versus the lower concentration at the other 2. So we've been looking a bit more at that. We've had data since January 18th. So this map, this time series here is basically showing the blue dashed line is from that higher concentration site. And in general, it does read higher than the FEM, which is actually green on this map, and the other purple air. And sure enough, when I looked at a topographic map, I see that this star here is where that location is, right in a valley, as indicated by our New Brunswick Lung partner. So next steps, we will continue to evaluate the small sensors, hope that the technology progresses for ozone and NO2, continue to work on our correction factor. Like I said, nonlinear adjustments are likely needed for the low and high concentration range, continue our pilot with New Brunswick, and hope to engage our forecasters. We're going to introduce the data set to the forecasters this spring. They'll be aware of the data in New Brunswick. Hopefully I'll get some feedback from them after the summer to see if they found the data set useful. And then based on the results of the pilot, we'll consider other targeted deployments possibly throughout Atlantic Canada. And I have to acknowledge the team here, my colleagues in the West, Keith Jones, Corinne Schiller, and Matthew Parsons, Celine Odette from Health and Air Quality Forecast Services, the New Brunswick Lung Association, Barb McKinnon, Melanie Langell, and Elise Wilton, New Brunswick Environment, Eric Blanchard, Nova Scotia Environment, Stephanie McDougall, Matthew Seaboyer, and Cody Barnett, PEI Environment, Sean Ledgerwood, Glenn Robertson, Kenneth McDonald, Newfoundland Environment, Robert Redmond, and Morgan Mitchell, who you heard from earlier, we were lucky to have as a student in summer of 2020. And I'll be happy to take any questions.